So if we move on to our second chapter, which is about cohesive frictional soil. So up to now we have discussed the slope stability with respect to purely frictional and purely cohesive soil. Now this is the cohesive frictional soil, right? That means we have both strength components, right? Most of the time, so we use this both strength component in the analysis of slopes, so which is the most ideal way, right? Because in this previous method is for undrained analysis or undrained state of the embankment, which is made of generally clay soil, right? So so this the method of analysis of cohesive frictional soil, that means we have both C and P, right? C and P. So we use something called this Swedish method of slices, right? Swedish method of slices. So let's look at this Swedish method of slices, right? So the difference here is again there is a slip circle, as you can see. So this is the slip circle, and what we do is we divide this whole slip circles into few what we call slices, right? This is a one slice, like 2, 3, 4, right? Likewise we can divide this into several slices, right? And in general we can select one slice, let's say this one, and we can this slice number 3, right? We can find the stability of this slice, assess the stability of this slice. So now if we find out the forces act on this slice, right, so you can see that there are two reactions from both sides. We have two reactions, which is here. This is the enlarged version of this slice, right? You can see this is a curved surface, right? The bottom of the slice we have a curved surface, but if we divide this into very large number of slices, this surface will become approximately planar or linear, right? So this is that enlarged view of the one of the slice. Let's say this one, number 3, right? So we know there are two reactions. If this slip circle slides, right, we know this whole portion will slide, right? So this is a critical slip circle that most probably will slide, right? So when it slide, all these sliding sectors, right, or we call slices, will slide together. So therefore we know this R1 and R2 will be equal, right? So we know R1 and R2 are equal because there is no differential movement among the slices, right? They will move in the same way, right, as an intact soil mass. So the other forces that we have, now we know we have W, right? We have W, the weight of the slice. Let's say this angle right? This angle is alpha, right? Angle is alpha. Now due to this weight, we know there is a normal reaction, right? There is a normal reaction. Let's say this normal reaction is M, right? M. And also we know in the sliding direction there is a force, let's say T, due to the component of the weight, right? So if we take trigonometry, you know this angle is alpha, 90 minus alpha, so this becomes alpha. So this is alpha, and therefore this becomes 90 minus alpha. So we can conclude that this N is W cos alpha and T is W sine alpha. Right. So if we look at the disturbing forces, right? So what is the disturbing force? You know, the disturbing forces are created by this weight component T, right? Because this is sliding due to the weight of the slice, right? This component T, right? So which is T. So what about resisting force? The reason I say forces, because we have two strength components. One is C, other one is Phi. Now C we already know is created by the cohesion along the bottom or the slip surface, right? So C act on this slip surface. Let's say this length is L, right? Length is L. So we can say it is C into the length L, right? C into L. That is one component, C. What about Phi? Phi is created by this reaction, normal reaction. We know, just like in F equals mu R, right? We know mu is tan phi. We did this earlier, right? So therefore this part should be like in mu R we have N into friction tan phi. N tan phi. Right? So that is the resisting forces. Right? Now up to now we have only considered one slice. So if we consider total slices, all the slices, the equilibrium of all the slices, we can introduce our factor of safety, right? We can introduce the factor of safety. So if we take the equilibrium of all slices, right? Let's say we have n number of slices, 10 at n, right? So we can write total, we consider the equilibrium, right? So the factor of safety can be written as total resisting forces divided by total disturbing forces. So the total resisting forces, right? We have, let's say, n number of slices, right? So this L values, you can see these L values, and also if we take weights, right? These different slices have different weights, so therefore they will have different N and T values, right? All these slices have different N and T values, and also this length of the bottom surface will also be different. So therefore we have to take the each and every slice, these values of each and every slice, and we have to add them together. We have to add them. So this addition I'm going to write it as sigma, right? Like that, sigma. So if we take these cohesion parts, so I'm going to write sigma of these all CL values, and also I have to take sigma of this N into tan phi and P values, and finally at the end sigma of T values. Now the thing is, we know that this C value and phi value, C and P are all common to all these slices, right? They are common parameters. So if they are common parameters, we can take these parameters outside of the sigma sign, right? So we can write I'm going to write C outside, then we have sigma L, right? Sigma L plus, and tan T also common, sigma N, right? Like this, and we have sigma T. And what about this sigma L? Sigma L means we take all these L1, L2, L3, likewise all the L values, right? So all the L values comprised of, you can see, comprised of total length of the slip circle. Now we already know what is the total length of the slip circle, right? Because if this theta and this radius is r, then we know the total length will be r theta, just like we did in last formulation, right? So we can write this as C into r theta. Then we have, I'm going to write sigma N separately and into tan P. Then we have sigma T, right? So this is our factor of safety equation for this Swedish method of slices, right? Now in order to do this, this is not a straightforward calculation, right? Because we have, you can see several slices. So when we have a problem, it's better to tabulate this. So draw a table, right, and do it more organized fashion, right, to find this factor of safety. So the next thing we are going to do is how we can devise this or formulate this table and find the factor of safety in an organized manner. So to do that, I'm going to go into one of these examples, right? One of these examples, this one, right? It says we have actually two diagrams. One it says the embankment of figure is made up of soil. We have P value C. The soil on which the embankment sits have 5 C75. That means we have two values, right? It's embankment. So this is the embankment. This actually both these figures represent the same embankment, but the thing is, one slip circle is beneath the embankment, right? Beneath the hard surface, right? Other one is different. So this one is a deep or base failure. This one is a face failure, right? So this embankment have properties of P. Properties of P. P is 20 and C is 20. And this embankment, the soil that the embankment sits, that means this soil beneath this, right? So this is the soil. The foundation soil, right? So this have properties of P7, P7 and C of 75, right? So this example number 1, the slip circle, we have only this soil, so it is a much simpler one. But the second one, we have to consider both soils, right? You can see we need to consider both soils because some of these slices are located in both soils, right? Both soils. So that is the thing. But if we take this first one, which is a more simpler one, we have only one soil, so one P value and C value, and the slices are given 1, 2, 3, 4, right? So these tables represent those values, right? Slice number, angle to the horizontal, right? So the angle of horizontal is that alpha value, right? angle to the horizontal, that is alpha value. So alpha values are given for each slice, and the area is also given. So area of each slice is given, and also for both soils it says gamma is 19.3. Gamma is 19.3. For example, if we multiply the area with gamma, we get the weight of each slice, right? Weight of each slice. So let's see how we can show this in a table and calculate. Use the calculation to find the factor of safety. So here so this is the same slice number alpha, which is the angle, and area is given. So what we need here is firstly weight or W, right? So to calculate W, we know we have to multiply this area value by 19.3. From that we get W, right? So now we have the weight of each slice, right? From the weight we should be able to calculate this T and N value. T and N value. So let's say capital N. So what is capital N? Capital N is W cos alpha. You can see W cos alpha, and T is W sin alpha. So we can write it should be W multiplied by cosine, but remember this in Excel we need to enter the radian value, right? So I'm going to write cosine in that radians, again that value, there should be 2 brackets, right? So for example, W cos 0 is same value, because we know cos 0 is 1, right? So we get our N values. That column is done. Then we have T. So we need to calculate T. T, we know it should be the weight into W sin alpha. Sin again should be in radians, and that alpha value, therefore now we have all N value, T value likewise, right? So in order to calculate this, we need N tan phi also, right? Because sigma T we can calculate by adding all these cells. So one thing we need is sigma N tan phi, or we can just take sigma N, right? So actually this table is enough to calculate our factor of safety, because all the others are we can calculate manually, right? So we can take sigma N, which is this part, sum of these, and again here we have sum of T. Sum of right. Now we have our sigma N and sigma T. This is sigma N and this is sigma T, right? Now we can apply our factor of safety equation. So this is the equation. C is already given as 20 and R is 9, as I remember. No, R is 10.7, theta is 76, and C value is 20. T value is 20. Okay. So to calculate this, so C is 20, R is 10.7, theta is 76, again in radians, 580 plus. Now sigma n, what is our sigma n value? Sigma n is 529, approximately 529, should be multiplied by tan 20. T value is 20. Divide by sigma t. So what is sigma t? 267. 267. So by dividing this, we get the factor of safety value. So with this calculation, you will get somewhere around 1.6. Check the value again by yourself. Okay. So this is the method that we use to calculate the factor of safety using Swedish method of slices. It is very simple. Just you have to do is follow the steps correctly, so you can find the factor of safety value by using the table. So if I remind you again about the table, we need slice number, alpha, area. If you know W directly, then you can get rid of this column, just add W. The important parts are this N and T. Once you know N and T, you can find this. If this R and theta is not given, we should be able to find these L values, right? These L values of each and every slice. So therefore, you can replace it with L value, right? There should be another column for L value like L1, L2, L3, L4. So finally, you can get the sum, right? So some modifications to be made when depending on the problem, but generally it is we use the same tabulated fashion for find the factor of safety. So hope you understood the process of Swedish method of slices. So I'll follow this up with some examples again, because we have for example this one, which is little bit complicated, and some other knowledge that you need to understood, some of the things that you need to understood in order to be more accurate, and especially your engineering judgment when it comes to analyzing slopes. So in the next lecture I'm going to discuss that, but in the meantime, for example, you can do this slip circle, right? You can try and find out factor of safety of this by yourselves. So till then, goodbye.